All right, let's get started today. We're going to be talking about generalized linear regression models using the rstanarm package. And so that means I have to tell you for about the 15th time so far this semester that I am a Columbia University employee. Columbia develops Stan. I use Stan for business-related stuff, and that creates an appearance of a conflict of interest over software that is free to download. Okay, so what is a generalized linear model aside from a generalization of the linear models that we were talking about on Tuesday, and except for maybe the prior stuff that you would already be familiar with. And so a generative model for a generalized linear model starts with priors on the intercept, coefficients, anything else, etc. Those can be most anything that you want if they're on the defined for the appropriate sample space. Then we have the so-called linear predictor, eta I, which is an endogenous unknown. So given alpha and beta and x, which is the exogenous known, eta is known exactly. But marginally, eta is not known because you don't know what alpha, beta, etc. are, only what your beliefs about them are. But anyway, plugging in values of alpha and beta, you just take alpha, that's basically your intercept, and then you sum up, there should be a k right there, xik. Take the kth predictor, multiply it by the kth coefficient, add those all up, and you have the so-called linear predictor for the ith observation. And this is going to hold for all n observations in your data set, which may differ from one observation to another because they have different values of the x variables, even though they're using, at least for this week, maybe next week too, I don't know, common values of alpha and beta for all observations. Next, we have another endogenous unknown, mu I, which is the conditional expectation of the outcome we're considering. Mu I is defined to be the inverse of the g function of eta I. So g function applied to mu yields eta. And this is called the link function. So that g inverse of eta, that is equal to mu I, and that is called the inverse link function. So g is a bijective function. It's confusing that g of mu is called the link function and g inverse of eta is called the inverse link function, because in a generative model, you're basically building this up so you can construct mu, so you need to be calling the inverse link function rather than the link function. So even though they're sort of the duals of each other, for our purposes, we're pretty much only going to be calling inverse link functions rather than the corresponding link functions. If that sounds confusing, it is, so you should blame the frequentist. Anyway, and then the final step of this is some conditional distribution for yi given its conditional expectation mu, which is a function of the x's and the alphas and the betas and the inverse g function that you're using. And so this conditional distribution of y given its conditional expectation can be a variety of things depending on what the sample space for your outcome is. Frequentists and Bayesians differ a bit in this, in that frequentists restrict themselves when they're doing, properly speaking to them, generalized linear models. These distributions for the outcome are going to come from the exponential family of distributions, which is a fairly wide family of distributions that includes the normal and the Bernoulli and a bunch of other things like that. Whereas from a Bayesian perspective, you can sort of think of a generalized linear model as anything that has this form, irrespective of what the distribution of the outcome given its expectation is. And this doesn't even necessarily have to be an expectation. It could be a median or something like that. Also, the priors, as we said above, on the parameters that go into the linear predictor can be anything, but typically in a regression context, these are going to be, weakly informative priors. Vast majority of the time, they're going to have a center at 0, and it's really just sort of a question of how much dispersion you want to put into your priors on those things. We'll talk about that a little bit more. But any model that sort of fits this pattern can be considered a generalized linear model. It is eta is a linear function of the parameters, and then you have one function which in general can be nonlinear, mapping eta to the conditional expectation. Now, if G inverse is the identity function and y given mu, there's also be a sigma in that case, is a Gaussian distribution, then the generalized linear model simplifies to just a linear model with Gaussian errors, and we'd be estimating the alpha and the beta and also the sigma. So there could be an additional nuisance parameter in there somewhere. So if G and G inverse is the identity function, y given mu is a normal distribution, then we just have a special case of a generalized linear model that we saw in the book and on Tuesday, linear model. But more often than not, when talking about a generalized linear model, we mean something with eta being a linear function of the parameters alpha and beta and all that, and G is some, or G inverse is some nonlinear function. And the nonlinearity certainly creates some confusion and interpretation and stuff like that, but allows us to model a bunch of outcomes that don't necessarily have a sample space, all real numbers, that come up a lot in social science. So what if y is a Bernoulli random variable? It's defined on 0 and 1. Then this G function would be taking our linear predictor and mapping it into the probability or the expectation for a Bernoulli random number, which is going to be something between 0 and 1, etc. And so this inverse link function assumes that they are enforces that the conditional expectation for this outcome variable, endogenous known variable, makes sense in that context. And this emphasizes a point made before that, all of these pieces kind of go together. In order to think about your parameters, what prior beliefs you might have on those, you have to know, what is the model that these parameters are being used in. And, that's going to entail some understanding of what your inverse link function is to know, how this mapping from linear predictor to conditional expectation works before you could say what would be reasonable values of the parameter and what would be, highly unlikely values of the parameter. Any questions about that general setup before we start to learn about a few special cases of a generalized linear model? Okay, so one example of a generalized linear model is a Logit model where the outcome is 0 or 1. There's a couple different ways to motivate a Logit model. So we have the first steps that we had before. Another way is, or one way to motivate a Logit model is to introduce an error that is drawn from a standard logistic distribution. And then we can define the sum of eta and epsilon to be this Greek letter, which is y. Set him straight, Christina. Epsilon. It looks kind of like y, which is why I use it. And then defining the outcome as being an indicator variable. If that is positive, then y is 1. If that is negative, then y is 0. So this doesn't exactly look like a generalized linear model yet, but it defines a posterior distribution for alpha, all the betas, and the error terms epsilon. So there's going to be n values of epsilon, one for each observation, an intercept, and k coefficients. And so that would certainly be a large posterior distribution to draw from, conditional on y. But analytically, you can integrate out all these epsilon terms from the posterior distribution, leaving yourself with just the posterior distribution for alpha and the betas, conditional on y and x and your priors and all that. And when you do so, then you get what may look to you a more conventional derivation of the Logit model, where we have an inverse link function, 1 divided by 1 plus e raised to the power negative eta sub I. Since e raised to the power of anything is going to be a positive number, we have 1 divided by something that's greater than 1. So mu, which is the probability parameter that goes into the Bernoulli likelihood, is going to be restricted to be between 0 and 1. And consequently, that makes sense for the probability parameter that is thought to generate the ith value of y. So here we have in math a generative model for, well, we kind of yada, 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 the priors, but mostly a generative model for Bernoulli outcomes that can depend on various values of x. So don't really worry about how you analytically integrate out all the epsilon variables. This is one that is much easier computationally because there's only k plus 1 parameters to be drawing from the posterior distribution of, as opposed to n plus k plus 1 parameters if you tried to do it this way. However, this form will have to return to like the last week in the semester because it is, you know, more convenient what you need to be doing if some of your outcome variables are missing, rather than what we're going to assume for today and for the next several weeks, that everything's just all fully observed. Andres.
I still have trouble understanding the part.
Yep.
Those 2 lines.
Right. So you've got the linear predictor. You got that. Then you have an error term assumed to be drawn from a logistic distribution. Add those 2 things together. If that's positive, then y is going to be 1. If that's negative, then y is going to be 0 under your generative model. So this is just an indicator function, just a true-false. Other questions about 2 ways of motivating a Logit model? Yeah. More often you see this in the context of economics, and this would more often be a normal distributed error, in which case we'll get a probit model. We'll talk about that briefly a little while later. But yeah, particularly in the case where it's normal, you can think of epsilon as utility for whatever success is, if this is like a choice people are making. Luke.
I still I need to give an example of what the lowercase answer. The position of a hierarchical model, you could have errors at the high level.
Yes. So this model is presumed to be flat, which is a sort of simplistic starting point. But you can think about the epsilons as being noise in the utility for whatever y is that isn't being explained by your x's. And it's being drawn independent of everything else. So if that assumption fails, then the posterior distribution of alpha and beta is going to be compromised. But anyway, basically utility noise. Another thing that I should point out is that in this formulation of the model, if I multiplied both sides of this equation by any positive constant, I would get the same observable y's. I would just be increasing the spread of the epsilons. And so that's why I have to fix the scale of the logistic distribution to be 1, because otherwise the scale of this would not be identified by the data. So the data are consistent with any scale. So just, for convenience, we fix it to 1 in order to have a model that we can actually estimate. Questions? All right. Let's see a generative model in Stan code. So I'm actually going to do both forms of it here. This is the first with sort of latent utility. So I'm going to have a S and I'm going to have an X. X is a vector that has n rows. I'm going to create a matrix that's S by n to hold my prior predictions, 1 for each observation that I have, and S simulations. So I go into my loop, putting a normal 0, 3 prior on alpha, normal 0, 1.5 prior on beta, loop over my observations, and here I've sort of, this term in parentheses here constitutes upsilon. If that's greater than 0, this is going to be 1. If that's less than 0, this is going to be 0. It gets stuffed into the appropriate column of my out matrix, and then I return. So then I could look to see whether these predictions for the outcome have a distribution that seems reasonable given the priors that I have here. So you might ask yourself, well, if this is just sort of a generic X, how could I possibly know that a normal 0 with standard deviation 1.5 prior is appropriate as a coefficient for that X? And the answer is perhaps surprisingly easy. That if you don't know what X is, ordinarily you would, but if you don't feel like you have a whole lot of information as to what these particular coefficients in this model are likely to be and unlikely to be, then just think of the distribution of logit coefficients in logit models that you've seen over your entire lifetime. Like, just imagine that marginal distribution and use that for your prior. So, for example, in 2008, when John McCain ran for president against Barack Obama, it turned out to be the case that the proportion of white people voting for Obama was low 40s, low to mid 40%. And the proportion of otherwise equivalent black people who voted for Obama was mid to high 90s. So in other words, sort of the white-black variable that you might put in a model like that shifted the probability from like 0.43 to 0.96 or something like that. And that corresponds to a shift in eta of about 3 1/4, 3 1/3, 3 1/2, something like that. And so that was a shift of more than 3. But that is probably the biggest coefficient in a logit model in the history of social science. Like, there is probably no X that you could put in your model for your master's thesis or whatever that would have as big an effect on something relating to the social sciences as the race variable between the first African American who ever got nominated for a major party versus John McCain, who's sort of typical old white guy who's been nominated for the president by every party going back to the 1800s, etc. And so the phraseology on your postcard that you send to people and remind them to vote is probably going to have not as big an effect as race did in the 2008 election. And so if, you know, my standard deviation here is 1.5, two standard deviations would be about 3. So I'm giving this like a 1% probability as being as big a deal as race was in the 2008 election. And that's entirely reasonable. In fact, I could probably make this smaller without even knowing what X is. And you could too. Anybody with the brain could. Same thing with generative model with the other form of a logit. So start off the same. And there's actually a function called Bernoulli_logit_RNG in the StanMath library. You just give it eta, and it will draw a 1 or 0 with the appropriate probability. This is equivalent but more efficient than drawing from a Bernoulli random number generator function, passing eta to the inverse logit function in order to get a value for the conditional expectation between 0 and 1. But you want to use these compound forms for computational reasons whenever they exist, and they do in the case of a Bernoulli logit. Questions about that? Sebastian?
This is kind of, sorry, now let's go back to the part.
This part?
Yeah. So part of the idea with this kind of prior is you're almost saying to data, you have to be really convincing if you're trying to tell me if there's such an extreme effect. You're making it less likely that your posterior is going to show as extreme.
That is true. So like, you know, 1% probability that it could be like as big as race was in the 2008 election. Yeah.
Does that also apply to sort of does everything get shrunk closer to the null, or just the extreme effects become less likely?
I mean, it's a whole distribution.
Yeah.
So you're basically saying, you know, there's a very, you know, 2/3 probability that it's going to be between -1.5 and 1.5, and like a 1/6 probability it's going to be less, a 1/6 probability that it's going to be more. It's symmetric around 0, but it is basically just capturing what I remember as being like typical values of coefficients in logit models. Now, if I actually knew what X was, I could probably come up with something more appropriate. But just in general, this is not going to be super inappropriate. Unless you're talking to the ghost of Fisher, in which case it's inappropriate to express your prior beliefs about anything. But I think, you know, that's diminished today. And those that do sort of push this idea that, oh, well, science should be objective, they really don't mean objective in Fisher's sense, that you don't inject like any information at all. What they really mean is that the researcher doing the analysis should be neutral. Like if I'm trying to estimate the treatment effect of something, having a prior that is centered on 0 and symmetric is neutral, equal probability of being positive or negative. It's more likely to be small than it is to be big. But it's not as if there's no information being transmitted there. But it's really just information about the scale of plausible effects, which for most things in the social sciences, particularly psychology, are very small. That's just kind of way social science research is. Unless you're the first African-American running for president or getting nominated. Questions about that? Nicole?
So along the lines of being objective as a researcher, what if you have subjective beliefs? Still okay to put them as your prior site. With the North Carolina police,
yeah.
What if I thought that they were extremely racist and I centered on like 6?
That's totally fine for what you believe. Yes. If you wanted to publish that, or you wanted to bring Title VII, if we had, you know, that Voting Rights Act thing, if we still had that, then you might have to sort of remove yourself from that a little bit, but it's still, you know, I think entirely reasonable for the Stanford people who wrote that paper to put the priors they did, because even though they were neutral and symmetric and everything like that, they had enough variance to them, so they weren't implying, you know, we're sure that all the police departments are, you know, doing things like they should. Left open considerable possibility that they might not be. And that was, you know, if you believe their model, really obvious in the posterior distribution once you condition on so much data. And, you know, even a lot of social science data sets are less, but once you condition on them, the things in the posterior distribution tend to be pretty clear. Sebastian.
Going back, so then if for example, your question was less about testing hypothesis, but more of an effect estimate, then might it make a lot more sense to have your prior hat of not zero?
It
like
could.
The literature says it's
Right. And so if you had a good previous study with different data, then using the conclusions of that study to inform your prior when you try to replicate that study, entirely reasonable. If the study was good to begin with, and it's difficult if that study, even if it was sort of good in some sense, if they used a frequentist estimator to try to take the frequentist estimates and make it into a Bayesian prior, I mean, you can get by, but it doesn't sort of come with enough information to just be like, oh, what is that posterior distribution? I'll make a histogram. What does that look like? And that's my prior, because you don't get a posterior distribution if they were just using maximum likelihood. So you get like a point estimate and a standard error and some confidence intervals, and you kind of have to wave your hands. Other questions? Okay, so how will we estimate one of these using the stan underscore GLM function and the rstanarm package, which unsurprisingly has the same syntax for the most part as the GLM function that comes with R. There's an example from the reading using national election study data to predict whether someone will vote Republican in a presidential election. So the income variable is categorical, like 1, 2, 3, 4, 5. So I'm going to coerce that to a factor. In the book, it just treats that as continuous. Don't do that. Also, I'm going to rescale age instead of being just number of years since you were born, number of decades since you were born. And that is mostly for interpretability and for reasonableness of prior. So if we're thinking about the effect of age on the probability that you vote Republican in a presidential election, a 1 year difference is, you know, if you have two people who differ by 1 year and otherwise the same, the probability that they vote for a Republican is going to be very similar. So we basically, I'm changing the units from years to decades so that it's, you know, you see a bigger difference between two people who are otherwise the same, but they're 10 years apart in age, which, you know, you can start to pick something up there. Anyway, stan underscore GLM, you put in your formula. Here I put age, the square of age, so allowing that to be nonlinear with respect to age, although it's linear with respect to these coefficients. The income factor variable, when you put it in a formula like this, it'll make a bunch of dummy variables relative to reference category, which in this case will be the poorest quintile or whatever it may be, and a dummy variable indicate whether the voter is white. We specify the name of the data set, which is NES. To specify a Logit model, we do family equal binomial, link equal Logit. Link equal Logit is actually the default, so you don't have to specify that, but it's good to be explicit about things because there's other link functions that are supported for binomial models. I'm going to restrict this to the subset year 1992. National election study has been going on every 2 years or every 4 years for extremely long time. Those of you who are not in political science, it's one of the very basic data sets in American politics. And lastly, I specify QR equal true. Why do I do that? So if you're going to use the default priors, which in Stan GLM is a normal distribution, then it's also good to specify the argument, although it's not the default, QR equal true. That gets you usually better computational performance, better effective sample size, often less time that it takes to get the posterior distribution. This only takes a few seconds. But the main thing is you get a better effective sample size when you do this for reasons that I'll have to explain like after spring break, because it involves some stuff in matrix algebra. That guy.
So are you taking the default priors here?
Yes. Normal. So they're like normal with a scale that it tries to figure out internally what would be best. I think by default it's like 2.5.
So if you were, you can specify them. You
Yes.
aren't doing it.
Right. And ordinarily, most people don't, like, because normal with the center of 0. And if you do QR equal false, which is the default, it will interpret the standard deviation of your prior in terms of standardized units. So it does some rescaling stuff internally in order to try to make it reasonable. But anyway, if you're not going to change the default, and most people don't, do change the default on QR to true, you're going to get better effective sample size, usually. Okay. So, all right. Here is the output that you would see if you do print post. Digits equal 2. By default, digits is 1, mostly because Andrew doesn't think people should be looking past the first decimal point anyway. But you know, when you see frequentist stuff, it's entirely common to see a table like this, and it'll have 8 decimal points for, you know, one of these estimated coefficients, and that's silly in part because no one really cares about the 8th decimal point, but it's silly in this context because, you know, we're doing a default number of MCMC iterations. By default, it's 4,000, and with 4,000 random draws from the posterior distribution, even though Stan is super efficient, so your effective sample size might be 4,500, 5,000 or something like that. Even with like 5,000 effective draws, it's hard to estimate the 3rd decimal point with a whole lot of precision. Like if it was really important to estimate the 3rd decimal point, well, you would need to be doing like 20,000 draws or something like that. But ordinarily, that's, you know, we don't care about that much precision, and so you don't need that many effective samples in order to be getting like the numbers on either side of the decimal point, you know, right, according to the analytical posterior distribution, which we can't even compute anyway because we can't do the integrals. So, you know, we get these. I talked about posterior median, posterior standard deviation. It says some stuff about the model. Also gives you the distribution of the sample average of the posterior predictive distribution for Y. So for these 1,356 people in my data set here that voted in 1992, it's saying that the average prediction among those people, average over the 1,356 people, has a median of 0.35 and a standard deviation of 0.02. So you're predicting the votes share for the Republican candidate, which was George Bush the elder, to be 0.35, which is actually pretty similar to what actually went on, because that was one of the rare elections where we had 3 somewhat credible candidates: Bill Clinton, who obviously won, and Ross Perot, who ran as sort of a third party, even though he made a party for himself called the Reform Party candidate, and he got like 20% of the vote nationwide. So that was rare, but that is a good way to check whether your model is predicting something reasonable by looking at the bottom here. All right. So how would we interpret the coefficient on age here? Oh, Rishika.
Why does the average have a median?
All right. Okay. So there's a lot of words going on here. We got posterior distribution of like alpha and beta and all that. We've got the predictions implied by those alpha and beta. So that's going to be 0 and 1 with some probability, depending on your age and your income and the fact that you're white and that stuff. Okay, so we have that for each person in the data set. So imagine you all are the data set. And then I average over the room. That has a posterior distribution with a median of 0.35 and a 0.02. So the averaging is over people. The median is the median of that distribution, and it has a small standard deviation. Because I don't know for sure what the alpha and betas are. Okay, how will we interpret age? How does that affect the probability of voting for George Bush? Really?
We ran the model increase age by 1 and circuit distributions.
Right. But if we just sort of had a quick look at this, what would we say?
Be 1 decade older. 1 decade older.
Yeah, 1 decade older.
Assuming all other variables.
Uh-huh.
Comparing two people where all other variables would be 1 decade older, associated with 29% less likely.
Does that make sense?
No.
A mystery. Because old timers are more likely to vote for the Republican Party in the United States. So that is something that is inconsistent with the prior beliefs that you actually have, but didn't get reflected in the default priors that got used here. But where you're making a mistake is this idea of, well, two people who are 1 decade apart, otherwise the same, they can't be the same on the age squared variable. And so although this is negative, this is positive. So each decade in spread, the coefficient on age goes down, or goes.
So if you're the older part of 1 decade, and you're
Or if you're in an older decade, like 80 years old,
right,
compared to someone who's in their 20s, it's all going to be down. And so the answer to the question is really what Merlin said. Game out the scenario and summarize or plot the distribution implied by your model to the question that your model should have an answer to. So, you know, baseline. Here we use posterior lin-pred rather than posterior predict. So posterior predict, or a predictive distribution in general, will be of observables. So it will spit out zeros and ones. And those zeros and ones are correct. They're going to be in the right proportion, but it's sort of a noisy indicator of the underlying probability or utility to vote for George Bush. And so we can just deal with the posterior distribution of mu directly in a Bernoulli model. It gets complicated like in a normal model because there's error, standard deviation sigma that we also have to take into account. So posterior predict is basically always going to be giving you the right thing, but it's not as always easy to use. And so models that don't have nuisance parameters, posterior lin-pred with transport equal true, gets the posterior distribution applying the inverse link function to eta evaluated at the posterior distribution of alpha and beta. Then you get the same data frame that you used to create this, just NES, increase everybody's age by 1 decade, get the corresponding predictions with new data equal ND, again, transfer equal true. And you make just a histogram of the difference in predictions between two people who differ by a decade, and now you're getting the posterior distribution over all 1,386 people in the sample for this hypothetical scenario. And we see that the change in probability, we believe it has this distribution after seeing the data. It's certainly highly concentrated near 0, perhaps a bit more likely to be positive than negative, but certainly any number between negative 0.5 and positive 0.1 has a good bit of probability associated with it. And so the bottom line is we don't know that precisely what the effective age was on that election, even given the data that we have. And for that election, it was a little bit weird because Ross Perot was another old white guy. So, you know, old people had 2 old white guys to choose from, plus Bill Clinton, who wasn't that old yet. And so, and Ross Perot is kind of like an older version of Mitt Romney a little bit. And so he was kind of a government outsider also. Anyway, a lot of old people really liked Perot. And so the effective age in this particular election, remember, we're only talking about the data that we have, was maybe a bit different than what we think age usually is in US elections. So we don't really know if it's positive or negative that well, but we do know it's not 0.2. The change in probability is not 0.2, and it's not negative 0.1. So we actually know a lot. It's reasonably concentrated on 0. Now, you know, most people doing this from a frequentist perspective, they would get a table that looks just like this, except it's called point estimate and standard error. And they would mess up what is the effective age on the probability of voting for the Republican candidate for president in that election. Like, the vast majority would mess that up because they don't have a mechanism to, you know, plumb all this through the model and taking into account their uncertainty in order to get out something like this, because you don't really get posterior uncertainty from a frequentist thing. All these standard errors tell you as well how much would the distribution of the estimates differ if you took 1,300 people over and over and over again and estimated this thing, which is a weird way of doing it, not really what you want, and not lending itself to just, you know, put the whole posterior distribution through the predictive process and then get in the units that are most reasonable to talk about a distribution of your beliefs as to what would happen, you know, 2 people separated in age by a decade. This is a change in probability, whereas this is this sort of nonlinear polynomial thing in terms of log odds. So why are we even talking about log odds for expressing substantive conclusions about something in, you know, social science, when whoever you're talking to or whoever is doing the talking has really no conception for what a log odds is in the first place? It's just a modeling trick that allows us to express things in terms of a linear predictor and then apply this not too confusing, but, you know, confusing for a lot of people, nonlinear function mapping log odds to probability. So if a model will tell us, you know, our beliefs in terms of probability, which everybody basically understands intuitively, then put your conclusion in terms of probability and put your conclusion, you know, for exactly the question that you want to answer, as opposed to, you know, saying, well, we failed to reject the null hypothesis that the main effect of age is 0, versus we are pretty sure it's near 0. The probability that it's between negative 0.05 and positive 0.1 is probably, you know, greater than 90%. Things like that. Christina. Transform equal true. Transform equal false would give you the linear predictor. Transform equal true gives you the conditional expectation. Or do it with transform equal false and then just take that and do 1 divided by 1 plus e to the negative that. That's all it is. Questions?
So
Nathan, number 1.
when we're applying like different length functions, if that happens, then it would just know based on what's happened before which transform.
Yeah, so it's taking the object that came out of the model you estimated. So it's stored in there. Now that's when you do stuff with rstanarm, BRMS, etc., that come with Stan models, and so it knows what the model is. When you and by the time we get to April are doing your own Stan models in the Stan language, then you know what the model is, but R doesn't. So R doesn't have a way of like reading a Stan model and knowing what was going on in. So you would have to do steps like this yourself, where you create the posterior distribution of the linear predictor. You map it through the inverse link function. So now you're talking about the distribution of the conditional expectation. Other questions about that? Andres?
It's a change product for an individual, right? Like,
Yeah.
it's not the like. Is the change product for an individual voting for?
Yes. So did I put it here? I did not. Posterior linpred is going to return a matrix that is S by N. So 4,000 divided by 1,356. So each column of baseline and each column of plus 10 represents the conditional expectation for each person. So person number 2, person number 6, etc. What I did here was just kind of mush them together. So really, this is the difference in probability for like an average person. If you are averaging over people in the data set. I mean, you could also do this for a particular person. Remember, when you have a linear predictor and then you do a nonlinear transformation to it, you can't just look at one coefficient in isolation either. The probability depends on what you set the other values of x to. So if we wanted to, we could say, well, what's the expected difference in probability for 2 people who are a decade apart, otherwise the same, but they're both middle income and white. So we could fix those values of the predictors, go through the same thing, and get a somewhat different probability distribution for middle income white people. What's the effect of a decade age gap? This is accumulating over all kinds of people, but with a hypothetical 10-year spread in their age. Everything else is the same. Because this is a reasonable sample, these people are kind of in proportion to the population of voters. Other questions? Okay. We might ask ourselves, how much did the default priors matter? So over here on the right, we have the distribution from the priors on each of these variables that it came up with after doing the QR thing and all the other stuff that it does. You can see for the most part, these are very wide. There's certainly the 90% intervals range from 10 to -10, which is like triple the effect of race in the 2008 election, etc. The one for age is a lot smaller, just because the scale of age squared is much bigger than these dummy variables, and so it sort of can't have a super big effect without, blowing up the whole thing. But of course, you see the posterior distribution of all these things. The scale, which is the same in both of these two plots, is totally out of whack. Like the 90% posterior interval, credible interval for each of these variables is less than the width of the dot for the posterior median here. So, I mean, if you wanted to look, you could look at the summary and get more clearly, what's the 90% credible interval or something like that. But when you condition on 1,300 observations, the posterior distribution is much more concentrated than any weakly informative prior distribution. Robert.
Why do we think such unrealistically wide priors? Is it that we have enough data that we know that even with these really wide priors, we're going to end up pretty precise?
Well, some people have more data than others. The default priors in rstanarm tend to be pretty wide. And that is more to do with the fact that we want to encourage frequentists to switch to using Bayesian estimation. And so a lot of choices in rstanarm, for example, making the syntax of stan GLM be, exactly the same as the syntax of GLM, using the same likelihoods, and then choosing default priors that frequentists or people who would otherwise use frequentist methods are less likely to strongly object to. But this was certainly, way wide, although it's, concentrated compared to what a lot of people think they want to do or feel they want to do. It doesn't really involve thinking of saying, I want, a uniform prior over the whole real number line. Like same probability as being, 5 as 5 billion or negative 5 billion. All these like completely unrealistic values for coefficients in a Logit model, they want to use the same as for all the reasonable ones, which is like really a subset of what we see here. So you definitely could tighten them down a lot to correspond to what, most anybody knows about election voting, with variables like this. Is there a question here? Follow-up question?
rstanarm doesn't take into account how much data we have.
No, the default priors do not hinge on the number of observations. They do hinge on what model you're using and some other stuff like that, but not n. No. So related to this, how do we, know what the priors were? What did they imply? So one thing that you can do with any estimating function in rstanarm is specify the non-default argument prior underscore PD equal true, which will draw from the model but not condition on the data. So just draw from the prior, and then you can call posterior predict, which is a bit of a misnomer if all you did here was really draw from the prior. But anyway, you can get draws of the prior predictive distribution using this. The update function just allows you to take a thing that you previously specified and change like one or however many arguments you want to. So prior underscore PD by default is false. So condition on the data, draw from the posterior distribution. But you set it to true, you can draw from the prior distribution and then get the predictions thereof. And so I did this a little bit out of order, but just to re-emphasize, the matrix that comes out of this consists of zeros and ones. So these are predictions of observables. It's going to have 4,000 rows, which is the default value for S, keeping 1,000 values for each of 4 Markov chains estimated with stan. And we have 1,356 observations. So we get predictions or a distribution of predictions for each individual in our data set. And then we can do what we want with every of those. And if we make a histogram of the row means, So taking the proportion over the rows, so you're left with 4,000 of them and getting sort of a prediction for the vote share for George Bush in this election, you can see these priors, which were way too wide for anyone reasonable, but not wide enough for a lot of frequentists, implies a predictive distribution for the zeros and the ones that is a bit absurd. High probability that George Bush would get like less than 10%. Equally high probability that he would get more than 90%. And lesser values all throughout the middle here, which anyone would know that in, you know, the United States or really in any majoritarian system, even though that was kind of three-party candidates running. But anyway, U.S. presidential elections are always between like 40% and 60% when there's only Republican and Democrat. And then with the Ross Perot, it made things a little bit weird. So it was less for everybody because he took about 20% of the vote. But anyway, this U-shaped distribution is ridiculous for predictions of a majoritarian election. We have like lots of theory, empirical experience, not just the United States, lots of other countries that have majoritarian elections, that it's like the opposite of this with concentration in the middle, and you almost never have an election in like a real majoritarian democracy system where one candidate gets like 90% of the votes. That's in like Russia and stuff. So you can see if you look, most people have difficulty with the looking part. You can see the implications of your priors. A lot of people think, I have no idea. I don't know how I would ever pick those. You can just try something and then evaluate the implications of that. And when you're way too wide, you get this U-shaped distribution on the predictions that might be appropriate for something, but I can't really think of anything in social science where that would be a reasonable distribution of beliefs. Like probably very close to 0 or probably very close to 1, unlikely to be anything in the middle. Because the sort of things that we tend to research as social scientists are the things that are, you know, contested or controversial, or things, you know, where the country is like divided in opinions about. And so, you know, even if you hadn't looked at the data, you could have said, you know, any presidential election between like credible candidates is going to be between 0.3 and 0.7, if not 0.4 and 0.6, something like that. Not this. Now, this was totally fine because, you know, it still put like a decent amount of non-zero probability here. And then we updated it with a lot, but not a huge number of observations. And so if we posterior predict off after conditioning the data, then we end up with a distribution of this histogram constructed in the same way, but now off the posterior predicted distribution rather than the prior predicted distribution that looks like what your prior distribution or prior predictive distribution should have looked coming in. Becca.
Can you do the posterior limit spread for this too?
You could have, yes.
Because my sense is that that would actually, conditioning on the data normally would produce a distribution like that. Looks like a U.
Yeah.
The link, well,
Oh.
because for any given individual, it's likely that we are either quite certain they are or are not.
Yeah. So for an individual, that is a more reasonable thing to think. What was actually being histogrammed here was the row means.
But if you did link that wouldn't that give you that? It's giving you that.
Right. So if you did an average over people, now you would get the prior predictive distribution for, you know, someone who's 35, income level 4, not white, etc. And you could look to see if that looks reasonable. I mean, that should be like 0.8, 0.9 something voting for the Democrat. But you can see if that was reasonable. So by row meanings over the whole thing, I'm saying I'm going to define what's reasonable and not, you know, averaging over the whole country, which is certainly an easy-ish thing to do. But you could evaluate your predictions for individuals or types of individuals. Rashika.
I would like to understand what does it mean, as in like with a prior that doesn't seem as reasonable, you still end up getting a posterior distribution.
Right.
Makes sense.
It's unreasonable because there's too much probability out here, and these prior distributions are symmetric. So if you get like a couple prior draws that are a little bit out in the tails, but the tails are pretty heavy, then you get predictions for the vote share of a candidate that are very polarized. So in order to get something like kind of reasonable in the middle here, all the prior draws have to be pretty close to their dots. But there's a good chance that at least one of them isn't. And that's what gives you these overly extreme predictions of averages.
Any predictions based on this model would they do prior was not set time? I think are you evaluating the model?
Yeah. I think if you played around with the scales and did some non-default prior stuff, you could come up with a prior predictive distribution for the vote share that had this upside down U shape and was centered on, you know, 0.5 or something like that. Wouldn't be that difficult to do. In this case, you'd have to remember that Ross Perot was in it. So like the whole thing got shifted to the left a bit. But other than that, it would not be difficult for, you know, Daniel or whatever to come up with this or something very close to this as a prior distribution, even without seeing the data. And the data would then just confirm what any, you know, grad student in American politics should already know. Questions? You can also look, you know, what did your prior on the age coefficients imply after doing all the QR stuff. There's a Bayes plot package, which is good for plotting stuff for prior distributions, posterior distributions. It has a scatter thing, takes in a matrix of draws, in this case for the prior. And I say I want to plot the two age-related variables. These have a bit of a negative correlation. It looks more extreme than it is because this ranges from like -2 to 2, and this ranges from -30 to 30. But there is a bit of a negative correlation going on here, and that's to offset the positive correlation between age and age squared. So, you know, for any of this, you can figure out what your prior beliefs look like, what they imply, whether you're using the defaults or, you know, your own choices. Robert.
Wait, I'm sorry. What are we actually graphing here?
So put the prior, which was when I drew without conditioning on the data. Convert that to a matrix, which is going to have like 8 columns and 4,000 draws, one for each of the parameters. Pass that to MCMC scatter and say I want to plot the prior draws for the two age-related coefficients.
Okay.
So this is the coefficient on age and the coefficient on age squared under your default priors. These are not actual ages. No one is -15 years old. All right, we talked about probit models briefly. These just use normal distribution here rather than a logistic distribution for the noise and utility. Consequently, when you integrate out the upsilons, rather than getting the inverse logit link function that we got before, we get the probit inverse link function, which is just put eta into the standard normal CDF in order to get mu, which is the probability of success under a Bernoulli model. You can see stand code for drawing from that distribution. Just alpha plus beta xi, stuck into the phi function, which evaluates the standard normal CDF, passed to the Bernoulli RNG, and you get predictions of this under a probit model. That is going to be pretty similar to a logit, but here I use standard normal priors because the typical relationship between logit coefficients and probit coefficients is to multiply the probit coefficients by about 1.6. So if I multiplied up my priors by 1.6, I'd have my corresponding priors for a logit model. You can do either one. Probit's much more common in economics. Logit's much more common in statistics. Logit is computationally faster, but you probably wouldn't even notice for these. Another thing that we want to think about more going forward than immediately for today is how would we write the posterior kernel in the Stan language. So we knew how to draw from the prior predictive distribution. This is a simplified form of what Stan GLM with family equal binomial is doing. You've got a normal prior in log form for alpha, a normal prior in log form for beta. You're adding these because the logarithm of a product of the numerator of the right-hand side of base rule is the sum of the logarithms of their respective PDFs. And then there's a Bernoulli logit underscore LPMF, which is the log likelihood for a Bernoulli with a logit link function. And I just do y bar alpha plus beta x there. These functions that end in LPDF or LPMF, they can input vectors and arrays and whatnot, but they output scalars. So it's summing the log likelihood over all 1,356 observations here. So we have scalar, scalar, scalar. This is returning a single real number, which allows Stan to do its thing with no U-turn sampling and stuff like that. So actually writing the posterior kernel of a logit model or a probit model is not that hard. You're using, normals and Bernoullis or whatever, but you don't actually have to write out the mathematical function unless you're using a mathematical function that's not already in the Stan library. So just like you can use, d norm and d beta and stuff like that in R, there's corresponding Stan functions that do the same thing, although we're always using log units. So when we get into April, you're going to have to be using like little lines like this to define your posterior kernels in log units of these relatively simple models that are already like pre-written and pre-compiled using rstanarm in rstanarm. Okay, remaining time for today, let's consider a model for an outcome that is a count. So a generative model for this would have some priors on the parameters. That should be phi. We have a linear predictor for eta. We have noise that is distributed gamma with equal shape and rate. And then if we add on the noise to the linear predictor, put it into a Poisson model using the anti-log transformation to map from a real number to a positive number for the conditional expectation of y, we get this. If you integrate these noise terms out of the posterior distribution analytically, you get a generalized linear model where the outcome distribution is the so-called negative binomial distribution with conditional expectation e raised to the power of eta and reciprocal over dispersion parameter phi. So the Poisson is related to the negative binomial, but it's not exactly the same thing. Remember, the Poisson is the only distribution for which the expectation and the variance are the same number. That is usually inappropriate, albeit fascinating, in social science research, where the data, even when you condition on predictors, is going to tend to have more dispersion than in the conditional expectation. One way you can mitigate that is by introducing this extra reciprocal over dispersion parameter. using the negative binomial as your likelihood, which is a distribution for count outcomes that has greater variance than the conditional mean, which tends to be appropriate for a lot of things. You can see stand code to either draw from the prior predicted distribution or write down the posterior kernel using normal priors for the intercept and the coefficients, and an exponential prior with scale 1 for this reciprocal overdispersion parameter that allows you to better model the variation that tends to exist in count data. So you can use stand GLM with family equal Poisson to estimate a Poisson model, which assumes phi is infinity, or you can use stand underscore GLM dot NB to estimate a negative binomial model. This is one for an experiment done for roach eradication. So the outcome Y is the number of roaches observed after applying some treatment to the apartment building. There's some other variables here capturing how many roaches were observed before the experiment, etc. We get typical output, which is not really readily interpretable because we're using this anti-log inverse link function. So if you want to know, is the treatment effective? It sort of looks as if it might be negative, but that's not a sufficient amount of information. When you actually do the predictions, taking into account the fact that there's overdispersion in the outcome, we get a distribution that looks like this. So extremely heavy tails, and not obviously a negative effect on the number of roaches, etc. But bottom line, you're calling this in much the same way that you would call a negative binomial in the mass package to do it a frequentist way, or stand underscore GLM with family equal Poisson to estimate the more restrictive Poisson model for count outcomes. Again, doing this all with default priors, whereas you might want to use a more informative prior that reflects the fact that your treatment, whatever it may be, is extremely unlikely to yield more roaches. Like, it not maybe plausible, but not particularly likely that your chemical compound causes roaches to breed more. So you could possibly put more one-sided prior that says, well, either this does nothing, entirely plausible, or it has a tendency to kill roaches or sterilize them or whatever the treatment might be, so that there would be less observed roaches. Okay, that's it today. I will post the third homework tonight. It'll be due in a week using rstanarm and stuff like that. Oh, and there's a review session tomorrow afternoon at 4, IAB 270B. You don't have to come. It would certainly be advisable, but we'll be going, or the TAs will be going over some stuff from probability, some stuff from rstanarm, maybe a little bit on what Stan does. Hopefully we can get our demo running that shows Hamiltonian flow. So show up for that if you have time. If you can't make it, don't worry about it. We'll try to put it on YouTube again.